Okay, good morning. So for those of you online, I'll remind you until Tribby gets here that I'm running the whole show alone. And so I'll try to monitor the chat the best I can, okay? So I'll try to split my attention between the huge crowd that's filling the room right now and the copious audience out there in the virtual world. First reminder, t-shirts will be ordered today. Not everybody has placed an order, they're free. We'll order a few extras, but maybe they're your size and maybe they're not. So get those in. So what are we trying to do right now? We've been solving systems of linear equations. When A is square, same number of equations as we have unknowns. We've got that down. There exists a unique solution if and only if the determinant of A is not equal to 0. However, if we have a rectangular system, meaning we have, say, n equations, m unknowns, and n is not equal to m, we're kind of clueless right now about how to approach that with any kind of generality except just grinding through the equations, which isn't very appealing for Rob 101 students who like to be able to solve big things and do mathematics at the scale of life. So the tool, hey, there's Tribby. So online folks, I will have help in 2 minutes here. Good morning. The tool we're going to use is to move into looking at collections of vectors. So instead of just looking at vectors as things that show up as columns of matrices or right-hand sides of AX equals B, or as vectors of unknown, we will look at the set of all column vectors of length n, and we will call that Rn. So the length of the vector, I really wanted this one, is the same as Rn. So that's what the n designates as the length of the vector. And each of the components is just a real number. So it's something that we understand, square root of 2, Avogadro's number, pi, etc. Now we don't call elements of Rn column vectors, we simply call them vectors. Just assume that they're column, but if you want to call them column vectors, no one's going to slap your hand or anything. Then we looked at the algebra that we can do in Rn. So we know how to add two vectors. All we do is we add their respective components, and we know what addition means for real numbers, so we know how to then add two vectors. Also, if we take another constant in the reals, we can multiply that constant times a vector by multiplying it times each of the components. So this is giving us algebraic operations on the set of vectors of length n. And with that, you get the usual commutative law that it doesn't matter in what order you add the vectors. It's associative. If you have 3 of them and you add the first 2 of them first using this rule, and then you add a third vector to it, it's the same thing as if you added the last 2 first and then you added the third one. And the reason that works is because addition of real numbers satisfies all of those properties. So we're just taking properties of the reals, and if we use that as this is our definition of vector addition, and this is our definition of scalar times vector multiplication, we inherit the nice properties of numbers in the reals. And then we can identify columns of a n by m matrix as elements of Rn, because the columns of an n by m matrix are vectors, and they have length n. And so here's the jth column of a rectangular matrix which has n rows, and each of the columns is a vector in Rn. So we will take advantage of that when trying to do calculations. Okay, ready to move forward with this setting? Let's see what we can do. So our first concept today we're actually going for two concepts: linear combinations and linear independence. It's a pretty powerful vocabulary that will help you in discussing, so help us and you in the discussion of properties of linear equations. So a first definition then, which will be linear combinations. Is that a vector V in Rn is a linear combination of vectors V1, V2, Vm in Rn if there exist real numbers or scalars, alpha 1, alpha 2, alpha m, and so emphasize the reals. We'll just write down that they're in the reals. Such that, alpha 1 times V1 plus alpha 2 times V2 plus alpha m times Vm equals our original vector V. Oh, come on. Be nice. Okay, so if we can write V as a sum of vectors, then, so here's V, and we've written it as a sum of vectors with weights given by real numbers. V is said to be a linear combination. Then finite sums of the form. So if we just write down alpha 1 V1 plus alpha 2 V2 plus ... alpha m Vm. So finite sums like that are called linear combinations. Okay, seems like an arbitrary abstract definition, and then we'll just take it as that, and then we'll relate it to solutions of linear equations in a little bit. Okay, so writing V as a sum of other vectors, that says that V is a linear combination of those vectors, and any finite sum like that is just called a linear combination, so V is a linear combination then of these vectors here. I've got to really do better with my emphasize. Whoa, it's comedic this morning. Okay, let's move on to the examples. Maybe that will go better for me. Okay. If I take 2 times 6, 7, 8, minus 3 times the stunningly original vector 1, 2, 3, if you do the math, you get the vector 9, 8, 7, okay? So hence the vector 9, 8, 7 is a linear combination of the vectors 6, 7, 8, 1, 2, 3. Okay, so just illustrating the definition, I can write this vector was given to me as a linear combination of two other vectors, so by definition, it is a linear combination of those vectors. Now, also, the vector 3, 3.5, 4 is a linear combination of 6, 7, 8, and 1, 2, 3, because well, why is that true? Can I write 3, 3.5, and 4 as a linear combination of 6, 7, 8, and 1, 2, 3? Yes, I can, because 3, 3.5, and 4 is equal to 1/2 times the vector 6, 7, 8, plus 0 times the vector 1, 2, 3. Okay, so that's an allowed linear combination. It's any real number. 0 is still a real number. Okay. Then moreover, let's just get over the obvious and accept it. I can write the 0 vector as being 0 times 6, 7, 8, plus 0 times 1, 2, 3. Okay, I'm just doing component-wise arithmetic, so that all works out. Hence, 0, 0, 0 is a linear combination of 6, 7, 8, and 1, 2, 3. Okay, so any vectors that I can basically solve the equation, that vector is some real number, alpha times one vector plus another real number, alpha 2 or beta or gamma, whatever you want to call it, times the next vector. That's a linear combination. Now this is not problem as in difficulty, but question now, is the vector 1, 5, 3 a linear combination of the vectors 1, 2, 3 and 2, 1, 2. So let's see if we can figure out what this question means and then relate it to solving linear equations. Okay, I want to know if I can write 1, 5, 3 as a linear combination of the vectors 1, 2, 3, 2, 1, 2. Okay, so once again, I'm looking for coefficients times the given vector to reconstruct the one vector. So V is a linear combination of all of these if I can find real numbers to do that. Well, so let's write this down in terms of the definition. So solution by the definition of linear combination. And this is the part that people struggle with in the beginning when they're doing math, is just applying the definition. So we seek alpha 1, alpha 2 real numbers such that alpha 1 times 1, 2, 3 plus alpha 2 times 2, 1, 2 is equal to 1, 5, 3. Thrilling equation. That's how you approach testing if something is a linear combination. Okay, so we have 3 equations and 2 unknowns, right? Does it have a solution? Again, I see palm face, okay? That's okay. Let's attack it. Let's call this equation 1. So how can we attack this? Well, just note that 1 is equivalent to, we can write down this condition, alpha 1 times 1, 2 plus alpha 2 times 2, 1 equals 1, 5. We'll call that equation 2. And then this is really important, and the third equation, which is alpha 1 times 3 plus alpha 2 times 2 is equal to 3. Okay, have I done anything brilliant here? Not really, okay? I have 3 equations in 2 unknowns. That's the same thing as looking at 2 of the equations, which is what I've written down here, and then separating out the third equation, okay? It's the same set of equations. And we'll call this 3. Okay, so now, if alpha 1 and alpha 2 satisfy equation 2, then what do we have? This is the same thing as the matrix 1, 2, 2, 1 times alpha 1, alpha 2 equals 1, 5. So what's the determinant of this matrix? 1 times 1 minus 2 times 2. So it's minus 3, not equal to 0, right? We're just applying what we know about systems of linear equations. Okay, so conclusion. Equation 2 has a unique solution. Some boring hand computations, so I did them. I'll let you do them. Yield that this is the answer. Alpha 1, alpha 2 equal, and what were they? I forgot. Oh, 3 and 1, okay. There must be a minus 1 somewhere there, because that's not going to work, right? So, oh, Tribby, I think this should be minus 1. Hopefully that works. No. I did my inverse correctly, and I can't multiply. Oh, 3 and minus 1. Yep, I think this will work. 3 minus 2 is 1, and then 3 times 2 is 6, minus 1 is 5. Yes, there's my minus sign mistake. I found it. Okay, so there's the solution. So they're only boring when you do them wrong, okay? Now, that's only part of the conditions. We need alpha 1 and alpha 2 that satisfy all 3 of these equations. We now have an alpha 1 and alpha 2 that satisfy the first 2. So we must check so do they also satisfy our third equation, which was alpha 1, 3 alpha 1 plus 2 alpha 2 equals 3. Well, let's plug it in. 3 times 3 plus 2 times minus 1. Okay, so that's 9 minus 2, that equals 7, and that's not equal to 3. So hence, what can we conclude? What can we conclude about 153 being yes or no, a linear combination of 1, 2, 3 and 2, 1, 2? The answer is it's not, okay? There's no coefficients alpha 1 and alpha 2 that satisfy that, okay? Hence, 153 is not a linear combination of 1, 2, 3, and 2, 1, 2. Okay, so that calculation is super painful, and we're going to want to make that a much easier calculation. Okay, so just a remark. At the present time, checking if V in Rn can be written as a linear combination of some other set of vectors is tedious, and I'll put the remark, and error prone, because even I made a mistake, okay? Left off my minus sign. So we don't like methods like that, okay? So we're gonna have to come back and fix this. All we're doing right now is we have a definition. Linear combinations are just putting 3 times one vector and 11 times another one, minus 17 times this one, and 1 over pi times the other one. Can we find a solution to that set of equations? Okay, so we want to come back and fix that up a little bit. But let's take advantage of what we have so far and relate it to existence of solutions to AX equals B. Okay, let's see how our notion of linear combinations gets us partway to the answer of this question. So let's consider a system of n equations in m unknowns. Okay, so how should I write that? Well, I like matrices. A11, A12, dot, 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 A1M. Because I have m unknowns, I need m columns. A21, A22, dot, 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 A2M, dot, dot, AN1, AN2, dot, 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 ANM. X1, X2, XM, then I'll have a B1, a B2, dot, 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 and a Bn. Okay, so I'm going to start my numbering all over with this new topic, call that equation 1. That's A, and it's n by m. This is x, it is m by 1, and this is B, and it is n by 1. Okay, just emphasizing the sizes. Okay, we know how to multiply matrices. I'm going to treat X as a m by 1 matrix. That gives me a column vector, right? So can I multiply these? Well, A is n by m, x is m by 1, so the answer should be, so the m's match, and so I need to get an n by 1 vector, and look what I get. I get an n by 1 vector. So everything's correct in terms of matrix multiplication. Okay, so now, what do we get if we do our column times row form of matrix multiplication? Okay, I need to keep that there. Okay, here's a column. It multiplies by this row. Everybody agree? Here's a column. It multiplies by this row. It's not my fault the row is trivial because it's an m by 1 vector, okay? I can't be held accountable for that. It's still just a row times, a column times row. Here's the jth column, here's the jth row, and we just add them up. Okay, so I'm going to write that down. So it's equal to A11, A21, dot, 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 AN1 times X1 second column, second row, A12, A22, dot, 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 AN2 times X2 plus dot, 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 plus. Up to the last column, A1M, A2M, dot, 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 ANM. Wow, that's pretty ugly. Any better? A little bit. Times XM is equal to B1, B2, dot, 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 BM. Questions on how we got that beautiful formula? Row times column multiplication? No, makes it really hard to see that. Column times row multiplication makes it super easy to see this, okay? So what is this? Let me write it in a slightly different way. This constant I can bring out to the front. It doesn't change anything. So I can write this as x1 times the first column of A plus x2 times the second column of A plus xm times the nth column of A is equal to B. Question?
It should be Bn instead of M.
Bn, yes. Yes, there's n components in B. Whoops, why is that not erasing? Okay, my mistake, yep. We have n equations, n unknowns. M is the number of columns, n is the number of rows. Okay. So what is the left-hand side? It's a linear combination of the columns of A. Ooh. What is the right-hand side? B. So this equation says that B is a linear combination of the columns of A. So here's the fact, and then we'll go through it just a little bit. AX equals B has a solution if and only if B is a linear combination of the columns of A. Okay, so why does that hold once again? Why? Suppose that A times X bar equals B. So X bar is a solution. Okay, well, what is X bar? Let's just call it X bar 1, X bar 2, X bar M. And then we've already seen, I just write this out using column times rows, we get X bar 1 times the first column of A plus X bar 2 times the second column of A plus X bar M times the last column of A is equal to B. Hence, B is a linear combination of the columns. So if we have a solution, these are just numbers, 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 linear combination equal to B. Okay, so it's the same thing. And then on the other hand, suppose we have numbers alpha 1, A1 column plus alpha 2, A2 column, alpha M, AM column that's equal to B. Well, I can just stack those up. And we have a solution, call that double bar, to AX equals B. Okay, so solutions of AX equals B, and B being a linear combination of the columns of A, that's the same thing, completely equivalent. Okay, so when we get a nice test for checking that B can be written as a linear combination of the columns of A, then we'll have our necessary and sufficient condition for solutions to AX equals B. Okay, so that'll go way beyond the determinant being equal to 0. So, questions on linear combinations and how it relates to solutions of equations? Good time for those? No, we're nailing it. It's too easy. I'm beating a dead horse. I'm stroking a kitty because it's really perfect to be going into this much detail. Okay. Nobody in the classroom, for the record, wants to state one way or the other on that. Okay, so here's our next big topic, linear independence. Okay, so if you guys get down linear combinations and linear independence, it's sort of like 25% of linear algebra is right there, okay? I know it seems really trivial so far, and it's not that hard, but you got to still wrap your head around all this stuff, and that part is not easy to keep it all straight, okay? Anytime you're throwing a lot of definitions around, it's very easy to mess them up. It's like vocabulary. So a set of vectors v1, v2, vm in Rn is linearly independent the only set of real numbers alpha 1, alpha 2, alpha m satisfying the following equation: alpha 1 v1 plus alpha 2 v2 alpha m vm equals the zero vector. So let me emphasize, I'm saying the vectors add up to the zero vector. Okay, the only set of real numbers satisfying this, the set is alpha 1 equals 0, alpha 2 equals 0, alpha m equals 0. Okay, let's take this apart. It's clear alpha 1 equals 0, alpha 2 equals 0, dot, 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 alpha m equals 0. That will always add up to the zero vector. That's always a solution. So the question is, are there other solutions that are not trivial? So this is the trivial solution, all of them being 0. Okay? If that's the only way you can get the zero vector, then they're linearly independent. Otherwise, the vectors are linearly, whoops, let me write that in red, linearly dependent. Okay, so for emphasis, linear independence you do alpha 1, whoops. There needs to be some vectors that you're multiplying here. Alpha 2, v2, alpha m, vm equals 0 if and only if alpha 1, alpha 2, alpha m is equal to 0, 0, dot, 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 0. Okay, that's the only solution. Okay. So why call the other case linear dependence? Okay, so if I have a set that is not linearly independent, then I can find, so there exist alpha 1, alpha 2, alpha m, not all 0, such that I have alpha 1 times v1, alpha 2 times v2, dot, 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 alpha m times vm equals the 0 vector. Okay, so one of the alphas is not 0. Could be 2 of them, could be 3 of them. Let's just suppose it's alpha 1. Okay, well, then I can write alpha 1 times v1 is minus alpha 2 times v2 minus alpha 3 times v3 minus dot, 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 alpha m times vm. And then I can divide by alpha 1 because it's not equal to 0. And I get alpha 2 over alpha 1 times v2 minus alpha m over alpha 1 times vm. And thus at least one of the vectors can be expressed as a non-trivial linear combination of the other vectors. Okay, so being linearly independent says that if you pick one of the vectors out, you can't reconstruct it with combinations of the others. If it's linearly dependent, at least one of the vectors can be written as a combination of the remaining vectors, okay? So if the set is linearly independent, it's kind of the smallest it can be. If it's dependent, you can take one of them out and still by doing linear combinations, get everything that you would have had with the original set of vectors. It's too big, okay? So independence is kind of a minimality of the set of vectors. There's nothing extra that you couldn't recover by just doing linear combinations. Okay, so we'll start checking for linear combinations on Wednesday. And then we won't have to do as many definitions on Wednesday because now we've got the definitions, now we can have fun with them, okay? So today was let's get the definitions down. Thank you.